Hello. Hello. Good afternoon to all the participants. Uh, Today's session will start within 10 to 15 minutes. Good morning, sir. Balwinder, sir.
मॉर्निंग गुड मॉर्निंग
Good
साहिब
morning, sir. Morning, sir. Sir, 5-10 मिनट वेट कर लेते हैं.
हाँ ठीक
5
है
मिनट.
मैं ऑनलाइन हूँ जब भी स्टार्ट करना हो बता देना
ओके सर. ओके सर. थैंक यू सर. Okay. Good morning, all dear participants and Dr. Blinder Raj sir. I will give brief introduction about today's speaker, Dr. Balwinder Raj sir. Dr. Balwinder Raj is currently working as an associate professor in ECE department and IEEER Chandigarh. Earlier, he worked as assistant professor in NIT Jalandhar from 2012 to 2019. He did B.Tech in Electronics Engineering from PTU Jalandhar in 2004, M.Tech in Microelectronics from Punjab University Chandigarh in 2006, and PhD in VLSI Design from IIT Roorkee in 2010. For further research work, European Commission awarded him Mobility of Life Research Fellowship for postdoc research work in University of Rome, Italy in 2010 to 2011. He also worked as visiting researcher at KTH University, Sweden from October-November 2013, and also in Aalto University, Finland in June 2017. Dr. Raj received Best Teacher Award from IST in New Delhi in July 2013. Dr. Raj received Young Scientist Award from Punjab Academy of Sciences on 9th February 2015. Dr. Raj has authored and co-authored in 3 books, 8 book chapters, and more than 70 research papers in peer-reviewed international national journals and conferences. He guided 7 PhD students, and currently 5 PhD scholars are working with him. He guided more than 30 M.Tech students. His area of interest in research and classical, non-classical, nanoscale semiconductor devices modeling, Finland-based memory design, FinFET-based memory design, low-power VLSI design, digital analog VLSI design, and FPGA implementations. Thank you. Sir, please.
Okay, thank you. Thank you, Sahil, for this nice introduction. So, very good morning to all. So, first of all, I would like to thanks Dr. Mamta Khosla, Madam, and Dr. Ashish Raman, sir.
Good morning, sir.
Good morning, sir. Good morning.
क्या हाल चाल?
सब बढ़िया, फाइन.
बढ़िया. मैं थोड़ा सा लेट हो गया आज, थोड़ी ना तबीयत से खराब हो रखी थी.
Okay, no problem. So, can we start, sir?
Yeah. Please.
Okay. So, very good morning to all. I would like to thanks Dr. Mamta Khosla and Dr. Ashish Raman, sir, for giving me this opportunity to interact with all of you. So, let's start with the lecture. So, I would let me share my screen first. Okay, so I hope my PPT is visible to all of you.
Yes, sir. It is visible.
So my voice is also okay. It's audible.
Yes, sir. Okay.
Okay. So let's start with the lecture as Sahil mentioned and Bilvinder's Duel also. My title of my talk is FinFET Technology and Application. So FinFET is a nanoscale device. So it's you can say the advancement of MOSFET only. So under that, whatever the circuits or system we can design with the MOSFET, all those circuits and system we can design with the FinFET also. So applications are wide. So specifically in the logic design for the processors and memory cell design for our low power memory designs. These are the some of the applications of FinFET. Specifically, we can say logic and memory are the main application for the FinFET because of its nature of low power and high speed working. So we will focus more in this lecture on, we'll start with the introduction and then we will discuss the MOSFET and FinFET structures, how FinFET structure is derived from the MOSFET. Then SOI technology I will discuss briefly because FinFET is designed with the SOI technology with the silicon on insulator. Then how we can fabricate the FinFET, fabrication flow of specifically for the FinFET we will discuss. Then modeling and research trend in this area. And in the last, I will conclude my talk with the summary. So we can start with the MOSFET because all of the microelectronics or nanoelectronics available nowadays that is based on the MOSFET only. But the thing is, due to the high short channel effects and high doping required in the MOSFET, there are so many challenges in the MOSFET design. There are also high leakage current, power dissipation. So we cannot scale the MOSFET below 50 nanometer. So because of its short channel effect and power dissipation. To overcome the challenges we are facing in the MOSFET, we can go for the FinFET. FinFET is a double gate device and that can be designed both with the planar technology as well as with the vertical technology. So vertical nowadays is highly preferred technology because of its compact and high density. So with the FinFET, as I mentioned, MOSFET we can scale up to 50 nanometer. But if we have to go up to 10 nanometer or even below, we require the FinFET device. Even there are some other devices are also available. Those can simulated up to fabricated up to 10 nanometer. Like we have carbon nanotube field effect transistor, CNT FET, tunnel field effect transistor, nanowires, Pygate. So many structures are available, but those structures we can say still are under research and commercially products are not available. But FinFET technology is so matured nowadays. Even the iPhone or smartphone nowadays available in the market, they are having the FinFET technology with 14 nanometer. Commercially available products are there in the, but the CNT based or nanowire based products are not available now. Maybe in future, another 5 or 10 years later, we have the CNT based products also or nanowire based also, although they are more complex and high performance as compared to FinFET also. But in the current scenario, we can say products are available with the FinFET technology. So in the future also, we can say this FinFET technology will be very promising structure because of its scaling nature. So what are the advantages why we are scaling our devices from work 180 to 50 or below 50 to 10 nanometer? Because of its high speed, high density, low power, improved circuit performance, cost per function. And at the same time, as I mentioned, the challenges are in terms of subthreshold leakage current, gate dielectric leakage. So these can be overcome with the alternative device structures, novel device structures. And in the bulk devices, we have the high leakage current, power dissipation. Those can also be reduced with the help of high K dielectric material. Conventionally, traditionally, we are using the silicon dioxide as a dielectric material in these devices, but those material, although highly preferred in fabrication because of its easy fabrication and low cost, but due to the low dielectric constant value of silicon dioxide, the leakage current is high. As you know, the dielectric constant of silicon dioxide is just 3.9, but high K dielectric materials like HFO2, hafnium dioxide, or titanium dioxide, they are having the dielectric constant of around 20 or even from 20 to 100. There are some high dielectric materials are available. So with the high K dielectric, we can minimize the leakage current. Alternative techniques like metallic gate, ultra thin body FET, they are also available to reduce the leakage current. Let's briefly discuss what the MOS structures. Bulk MOSFET, I presume everyone aware about this MOSFET structure. We have a source, drain, and gate, and current flow from source to drain is controlled with the help of gate. So this is well available structure in all the textbook. So their operation is simple gate voltage control the flow of current under the channel. So how this is the work was how we came up with this ultra thin body structure with the additional layer of silicon dioxide under the source and drain. If we have this structure with the bulk MOSFET, there is a if we have a silicon substrate of P type, the source and drain will be N type, and there is a PN junction formulation in the source and body, drain and body. And if these PN junctions are forward wise, then the leakage current is high. So to mitigate this problem, additional layer of silicon dioxide is added here so that there is a breakdown in the path of source to body and drain to body, and this insulation layer minimize my leakage current. So there are some issues related to fabrication that we'll discuss later, and here this type of ultra thin body devices, they are fabricated with the SiFET technology. So let's come up with the double gate MOSFET and FinFET. So as its name indicates, double gate, we have two gate instead of single in the bulk MOSFET. Due to double gate, its driving capability is enhanced, or we can say that is doubled from the single gate, and the channel formulations also take place two times, front type and back side. So in this device can be used as a symmetrical double gate MOSFET or asymmetrical. When we say symmetrical gate structure, then this front gate and back gate both have the same oxide thickness, maybe same material, silicon dioxide, and when we say their thickness is also same material, same thickness, 1 nanometer, 1 nanometer, or 1.2 nanometer, 1.2 nanometer. In asymmetrical, we have a different thickness of the silicon dioxide, maybe one side 1 nanometer and another side 1.4 nanometer. So why we are using the different oxide thickness? Because as I mentioned, the challenges of leakage current in the bulk MOSFET, that we have to modify here. So if different oxide thickness is there, their work threshold voltage will be different. So threshold voltage is the main parameter that decides the on-off current, that decide my off current, leakage current. So if higher the threshold voltage is there, less will be the leakage current. If but I on is also less. To enhance on current, I have to keep my threshold voltage low. At the same time, I have to reduce the oxide thickness. At the same time, my leakage current will high. So we can say from here we can conclude, if I increase the VTH, my on current will reduce, and if we reduce the VTH, my on current increase. Okay, so with this trade-off, because I want to improve both speed and power, so I have required a asymmetrical structure. So with that, I can say if I have 1 nanometer oxide thickness here, I can improve my speed. With high oxide thickness here, I can reduce my leakage current. So this is a structure where we can improve both speed and power. But the thing is, with this type of structure, there is a problem of misalignment during fabrication. If these two structures are getting not aligned with each other, then there is a problem of high leakage, and then again the leakage problem is there, power dissipation problem is there. To rectify this problem, nowadays FinFET structures came into the picture, and this is known as a self-aligned structure where both the front gate, back gate, they are aligned with each other, and leakage current can be mitigated automatically. Another thing here, this is a SiFET technology silicon on insulator. We have a silicon dioxide layer here, and above this silicon dioxide, we have to grow whole the structure. So its structure is such a way, fabricated in such a way, their leakage current reduce automatically. We also use in the bottom side, bottom reflection coating. So that BARC used to minimize the leakage current and the bottom side also. So let me discuss briefly why we require the FinFET, what is the need of FinFET. As I mentioned, the planar MOSFET, they are approaching toward the practical limit and we cannot scale below 50 nanometer, and also high doping is required in the bulk MOSFET and FinFET. They can work for the low doping also. So with the high doping, there are so many other effects like surface roughness, scattering phenomena. So with those, our mobility degrade in the devices, but mobility is required to be high. So complex channel profile required to achieve the desired threshold voltage in a conventional devices, but with the FinFET or double gate MOSFET, we can, with the asymmetrical structure, we can go for the variation in the BTH also, both high and low. We can tune with the change in material, change in the dimensions of oxide thickness. Then in order to increase the gate control, we can also have in the FinFET by using the silicon fin with the more than one gate. Here I have given an example of double gate FinFET, but even we can go for the triple gate FinFET, quarter gate FinFET. So accordingly, if we keep on increasing the number of gates, its driving capability enhance further, but there are few challenges in terms of their interconnects and in terms of their driving the mathematical model, as well as in during fabrication also there are so many challenges if we increase the number of gates. So next is a tri-gate, three types of the double gate FinFET. So this is the planar double gate, where planar technology is where we go layer by layer. So we start also known as a serial type of fabrication. Sequentially, number of steps they followed. Like we have to take the silicon substrate, we have to grow the silicon dioxide, we have to apply the mask, there is a ion implantation, doping, there is a etching process, deposition, chemical vapor deposition, then there is a metal deposition. So all the fabrication process we have, steps we have, they run in the sequential form. But due to sequential form, as I mentioned in the double gate, if the gate are not aligned with each other, then leakage can enhance. So this planar technology having the limitation of high power dissipation. To mitigate this problem, this quasi CMOS structure literally simple for fabrication. This is used where this is also based on the SiFET technology, but instead of a sequential steps, there is a FinFET designed with some independent steps. Parallelly, we can do the various gate, source, drain structure. They can be grown independent from the one or the other. Here in the planar technology, we can say one step is dependent on the other. So in other way, we can say this is a parallel type of fabrication flow and this is a serial type of fabrication flow. Okay, so for the further improvement in terms of density, this type of vertical DG structure are used nowadays, and nowadays this vertical structure type of DG, they are highly you can say highly preferred in the research from its density point of view. How we increase the density in the vertical? So the question is how we can increase the density. Early days, you know, we have we got both NMOS and PMOS on the same wafer, because ultimately with these devices will be used to design the circuit. And in circuit, the simple circuit inverter, if we take example of inverter only, in inverter also we require one device, one is NMOS and there is PMOS, N FinFET, P FinFET. So early days we have in the planar technology, we have these devices on the same wafer in the same seed or same plane. Okay, so in the vertical, PMOS or NMOS, P FinFET, N FinFET, they can be stacked with one over the other. So double the density can be done in the vertical instead of previous we have in the conventional MOSFET technology, planar technology. Actually, the FinFET versus double gate MOSFET, although both are the new technology, but the FinFET that is highly suitable as its fabrication is also comparable with the conventional MOSFET technology. We need not to change our whole fabrication flow, but with the conventional available resources, we can fabricate the FinFET. But for the double gate fabrication complexity increase because of the it's a planar in nature. So these FinFET devices, they are highly used, we can say, in the preferred in the digital domain for the logic and memories, but for the double gate, they are highly used, we can say, in the analog domain, where we have to in the analog, where we focus on the gain and other parameter, but in the digital we focus on the parameter like its speed and power. And noise margin is also one of the crucial parameter. So in the double gate FinFET based, the two gates can be electrically isolated, mean we can have the asymmetrical structure, and that with the electrically isolated means they one independently can be biased, but in this case we require two power supply. For the front gate, if we have a oxide thickness of 1 nanometer, I may require the 1 volt supply. If I have a back gate bias voltage of 1. Oxide thickness of 1.2 or high K dielectric, I definitely require the high voltage to formulate the channel or to accumulate the carriers in the channel. In that case, we can say we require the separate power supply for both front and back gate. So in the that is the with the advantage, we can control the threshold voltage and leakage, but in the double gate, the different devising of two gate is difficult because of its it's a planar technology. Step by step we have to grow. Then another very important point in the FinFET is multi-fingers layout can be designed. Mean in the conventional MOSFET or even in the double gate MOSFET, there is a single channel that connecting my source and drain. But in the FinFET, fin is also act as a channel that connecting a source and drain, but multiple fins can be used to connect my source and drain. Conventionally, when the first FinFET was proposed in 2000 by University of California, Berkeley, one scientist known as his name is Chimin Hu from the University of California, Berkeley. He given the first FinFET structure, and that was a single fin based FinFET, means single channel connecting a source. Later on, the concept of multi fin came in the picture to enhance the further driving capability. So odd number of fins can be connected, means one fin can connect my source and drain, 3 fins can connect my source and drain, 5 fins or 7 fins. Here the important question is why we go for the odd number of fins only, why not even, why not 2, 4, 6 number of fins? Because if we have a even number of fins that are connecting my source and drain, then the parasitic capacitance in between these two fins, they have interference of one over the other, and due to that interference, the driving capability reduced instead of enhancement. Why we are using FinFET? I think everyone clear about it. It's not because of its high driving capability, but with the even number of fins, its driving capability reduced because of the parasitic capacitance. And those parasitic capacitances can be reduced if we have a odd number of fins connecting my source and drain, because in odd number of fins their capacitance in the capacitance ultimately what we have the charge only, and that charge can be cancelled by positive and negative potential on both the side, and the odd number of fins can cancel the charge and parasitic capacitance gets reduced automatically, but that concept cannot be applied in the even number of fins. So this is a very important aspect from the FinFET technology. Then the large packaging densities as compared to DC that we have already discussed, because we can stack in the vertical technology up and bottom both P and N, and driving capability packaging density can be enhanced as compared to DC. So let's further discuss a tri-gate FinFET. This is a structure for the tri-gate where we have a front gate and back gate, front gate, back gate, and top gate. So in these three sides, we have a oxide thickness of same maybe 1 nanometer, and bottom side, if we have a high oxide thickness of maybe 5 nanometer or 10 nanometer, then this is tri-gated FinFET, and this structure is highly used for the, we can say, integral, specifically for the logic design. Okay, so in the logic design, we require the switching speed must be as high as possible. So with the multi-gate, the switching speed can be enhanced so that my logical operation can be performed at a much faster speed. So this is a vertical FinFET. So in the vertical FinFET, there are different some of the parameters like fin height. This is the fin height that represent my channel width. Then we have this fin thickness that represent my silicon thickness of the device. Then we have a channel length LG, and that represent my distance in the source and drain. But if you see here, I have a source and drain, but this channel length is not completely covered with whole channel. So this is known as LG, and whole channel, this spacer, these are known as spacer, actually that is not covered with the gate. So this spacer technology used in the FinFET, but this was not used in the conventional devices. This is again another technique to minimize my leakage current, and this is also known as a underlap FinFET structure. So during fabrication, channel length, my gate can be two type. One is underlap structure and other is the overlap structure. So if we have a 30 nanometer technology, sometimes we write it's 32 nanometer, 20 nanometer, we sometimes we write 22 nanometer. These 2 nanometer, additional 2 nanometer of length of the device, that is used as an overlap on source side and drain side, because ultimately in the fabrication, we require the etching process to remove the unwanted materials, and in those fabrication unwanted material etching we do with the help of chemicals or with the applied voltage, two type of etching, wet etching or dry etching. Okay, so in the etching, the etching processes cannot be stored very precisely to make channel exactly 30 nanometer or 20 nanometer. So sometimes etching process may take some little bit longer time and longer a covered area, and my this spacer length can be increased or decreased accordingly. So that's why we mention LG different from effective L effective channel length. Effective channel length is different from the actual channel length available in the device. So in this W we calculate mostly with the help of 2 fin height plus fin thickness. This fin height, by we have taken 2 times to calculate its width, because it's a double gate device and the fin height is available for both the sides. So this is multiplied by 2 plus this parameter 1 of this. So in this way we calculate the W. So if we have a triple gate or quarter gate, accordingly the number fin height can be multiplied with the 3 or 4 to calculate the effective fin width. So next is the fin crystal orientation. So crystal orientation is the surface alignment. When we cut the wafer, so their surface alignment is in some particular direction. So that alignment is represented by 100, 11, 111 or 110. So this alignment, if we have a 110, then that is a highly using for the holes mobility can be enhanced. For the electron mobility enhancement, we use the surface this orientation 100. So in the FinFET, the beauty is this high mobility of electron and holes both can be achieved with the orientation of 110, but that is this type of orientation is not available in the conventional MOSFET. Why? The question is why not available in conventional? Because wafer is made of same material silicon, but because conventionally we are using a planar structure MOSFET, but here we are cutting this structure, we can say 3D type. Conventional devices, we consider the flow of current only from source to drain 1D or 2D. But FinFET being a gate available in all the sides, 2 gate, triple gate, quarter gate, we have to analyze its mobility not only from source to drain, but along the channel, but along the width also we analyze how the carriage movement is there. So in this these movement of carriers in the x-axis and y-axis can be analyzed with the different type of its orientation, and both NMOS and PMOS, they drive current is high in this FinFET orientation system. So next are the advantages of FinFET. I think it's clear to everyone now because of its self-aligned reduced resistance. So you can skip this part. So what are the challenges we have in the FinFET? So ultra thin silicon lithography is required to make its channel more small, its body thickness. So lithography process is the very important step in the whole fabrication, because lithography define my channel length. So there is another question, why we go in steps of technology scaling from 180 nanometer board to the 90 nanometer, 90 to 45, 45 to 32, 22. We are moving in the step, we are not going in between directly. So one thing is related to Moore's law, we have to double the component, so we scale accordingly. Second thing is more important is related to lithography, because lithography is the step in the fabrication that define my channel length. Okay, so lithography we cannot replace in the fabrication frequently, but during simulation, if we are doing work in the some tool like Centaurus or Seveco, we can even simulate at 15 nanometer or 18 nanometer or 25 nanometer. But for the fabrication point of view, we have to follow the standard steps given by ITRS. So for that, this is a challenge for the FinFET to design the thin silicon with the lithography. Another question is related to fin engineering. It's balancing in terms of in height, thickness, and channel length. As I mentioned in the previous, W is dependent on its channel. It's a fin height and width. Okay, so if I slightly change my fin height or fin thickness, its W will change. So in the conventional device, if you see my L and W by L ratio, they are independent. If I change my L, I can keep my width constant. But here, if I change the thickness or height, my width cannot be constant, that will vary automatically. So this is also one of the challenges in the FinFET. So we have to remotely control the fin width by changing the other fin engineering parameter like thickness, height, and length. So fin devices and component circuit modeling, to count for the quantum, we have to consider the quantum effects also. As I mentioned, the conventionally we are analyzing the current only one dimensional from source to drain. But in the FinFET, being a three-dimensional device, we have to analyze the current in the 3 dimensions. So that is a quantum effect we have to keep considering. So with the, if we consider the quantum effect in the device, then it's during simulation, if the conventional device at 45 nanometer, we simulate the simulation in the sense that may hardly take 5-10 minutes, but including the quantum effects, the same device simulation may take a 4-hour or 5-hour time period, because with the quantum effect, its analysis is more accurate, but at the same time, its behavior with the It's point by point means we are analyzing now a current flow at each meter instead of its classical theory. So next is the circuit and architecture design techniques we have to explore for high density, because only device improvement is not enough, but other circuit as well as interconnects we have to modify. Then only we can achieve the high density and high performance overall circuit and system architecture. So let's come up with the SOI technology. No. So what is SOI technology in the conventional planar MOSFET? If we have to enhance the device performance, we go for the strained silicon type of approach. So strained silicon approach is where we combine silicon and germanium together, because silicon and germanium both belong to group 4 element, and their outermost cell, then we can say their atomic structure, crystal structure, they are very similar to each other. So we can mix the material because both having the 4 free electron in their outermost cell. So there these material can be easily mix up to come up with a strained silicon. Why we are going mixing these atomic structure? Because silicon having their own benefit, germanium having their own benefit, and if you have to take benefit of both silicon and germanium, we can came up with there. But in the this strained silicon, we can enhance its driving capability, but we cannot control its power dissipation. So if we have to control the power dissipation, leakage can be alternate approach. In this is the silicon on insulator approach. In this above the silicon's substrate, we grow additional insulation layer. And with this SOI technology, the major benefit is the junction capacitance in the device is very low. So if the junction capacitance, parallelistic capacitance is low, then the device's performance in terms of its driving capability or movement of carriers that contribute in the leakage current, that can be improved. So leakage current, low leakage, and compatible fabrication techniques, they are used in the SOI technology. So SOI technology, they are classified in two forms. One is the partially depleted SOI technology MOSFET, and second is the fully depleted SOI MOSFET. So if we take example of the conventional MOSFET, in the conventional, our whole substrate is known as, this whole substrate is known as the body of the device, and the conventional MOSFET, this body is, because of the bulky in nature, its body effect is high, because we know sometimes in the textbook you might see this body from the backside that is connected with the ground, and there is a potential difference in the gate and source and body, and due to connecting this at the ground, but actually this body is not connected always with the ground, but that is connected with some positive or negative potential. Okay, so to mitigate this problem of body effect in this conventional devices, we go up with the partial depleted or fully depleted SOI devices, so that this body effect or this leakage current from the these devices within carrier movement can be minimized. So if we have a partial depleted devices, there is a one effect known as conic effect that is available in the partial depleted, but partial depleted are more having the high speed than the fully depleted. So fully depleted SOIs are having less speed, but they have their own pros and cons, and some different applications. If we have to go for the low cost at high speed, then we go for this partial depleted type SOI devices, and fully depleted SOI, they are if more and minute to its we can say its in terms of leakage current, because here this silicon device, silicon dioxide is here, but this device becomes more compact as compared to partially depleted. So if we have to go for high density, we go for the fully depleted SOIs. If we have to go for the high speed, free from the nick effect. What is nick effect? Nick effect is there is suddenly rise in the drain current in the device. So in the textbook IV characteristics, you might be seen in the saturation. There is after the linear region, there is a saturation region. Linear region is same in the partial and fully depleted devices as we have in the conventional, but during the saturation region, there is a slightly increase in the drain current as compared to the conventional. So that highly increase in the drain current is sometimes beneficial to have high on current, and at the same time that is having a limitation also. Because of that, there is some heat up, internal heat up in the device. So this is the difference in the partial and fully depleted SOI. So next is this SOI technology based devices. They can be designed with the multiple gates, single gate, double gate, triple gate, then quadruple gate, pi gate. So why we are going for these here, this is the buried oxide, this is the bottom layer, this is the silicon layer, then we have a buried oxide, silicon dioxide or any other oxide layer to make this box of SOI. So these both layered together formulate the box of silicon dioxide, and above this, these are the different devices grown on this silicon on insulator. Okay, so these devices again at the box can be designed with any technology, maybe planar type, maybe vertical type, or maybe hybrid type with the planar and vertical. So these type of SOI technology having the better performance. They are also having high tolerant to the scaling, and they are easy to integrate. So because the interconnection of these devices from circuit design point of view required to be integration required to be as simple as possible, so that their wiring tray or propagation tray both can be to control from the logical design point of view. Next, this is IBM introduced in the New York their FinFET device structure. They have given the separate their fin structure, the crystalline silicon. This is the view, and this is the gate separately. They have to propose with the small cut in the gate, so that they can design this FinFET with the hybrid technology. So separate silicon crystal with the insulated gate, and they can be combined up with the same. So this is the 10 picture of this fabricated FinFET with this the transmission electron microscope. Sometimes they give the internal view of the device, how their source and drain are connected, how much H height is there. So in this particular scanning electron microscope, they have given the height and T silicon 20 nanometer. Then its thickness vary with the oxide thickness 1.6 nanometer, then height is 65 nanometer. So these parameters, with these set of parameters, they have designed this FinFET on the buried oxide box. So with insulation SOI technology, this is so these are the different way of how you can go for a single box, then grow of the source and drain, and the separation in the source and drain. Then after this, there is a nitride, and for the spacer, as in the previous structure I have shown in the source and drain, the gate is not fully covered the whole distance from source and drain, but in the spacers is there, and in the spacer we add up some insulation material. In the low cost the low cost devices for simple application. This spacer may be silicon dioxide only, but where the some critical applications where the performance is more critical, then we apply this nitride spacer. So what is difference in nitride spacer and silicon dioxide spacer? One thing is related to its dielectric constant. Second thing is related to its temperature handling capacity. So nitride, they can handle the high temperature as compared to silicon dioxide, and they are having more reliable structure as compared to silicon dioxide as a spacer. So next is the multi-gate structure with the SOI devices. We have double gate FinFET. This is this part is known as a box, and of the double gate front and back gate can be grown, and the top side and bottom side we have a high oxide thickness. Then this triple gate type of SOI multi-gate MOSFET. So here we have three gate, all three sides having the same thickness. Then pi type structure is there. So in the triple gate, these spaces corners, sometimes leakage current is high to make the leakage current in the corner, that is also known as a in the FinFET one specific term is used, that is known as a corner effect, and that corner effect can be minimized with the pi type of structure. Then we have a quadrant type of gate. So this is the 2D view of all four structure: double gate, FinFET, tri-gate, and pi-gate, quadrant gate. So these type of structures here, this tri-gate, all side upside is same. This is a quadrant of quadrant. So these structure can be designed symmetrical and asymmetrical to make the devices. In the by sometimes we use this symmetrical, sometimes asymmetrical. How where we require symmetrical and asymmetrical, where we have to, that dependent on its application area. We are going for logical design or memory design. We are going for the high performance or low power. Accordingly, we selected the device dimensions and its structure and its symmetrical or asymmetrical. Then this is a pi type of structure. So the pi side, as I mentioned previously, they can minimize the corner effect. So in the pi side, these corners are slightly grown more in the silicon oxide layer. So the leakage current in these corners can be controlled by this gate insulator. This corner grown a little bit inside the oxide, basically to make a path of body to this outer surface, so that the corner can minimize the leakage that can be minimized. So next is the fabrication of the FinFET. Till now we have discussed the basics of FinFET, the FinFET structures, their different types, then different structures, single gate, double gate, triple gate, multi-gate MOSFET. Then we discussed the FinFET SOI technology, how partially depleted, fully depleted this technology can be used for the FinFET. So next we will discuss the FinFET fabrication, how we can fabricate these devices. So this is the FinFET fabrication process. That is there actually MOSFET fabrication and FinFET fabrication is similar. There first we have to it's a layout. If you see its layout, source and drain, and this is the gate connecting my source and drain, and this is another view of having a source gate and gate. So its fabrication is very much similar to the conventional devices, but the thing is its structural modification that we do in the design, that we have to do in the fabrication also. And in fabrication, the number of steps little bit increase from the conventional MOSFET, but the steps are the same that we do with the conventional MOSFET. So the first step of in the fabrication of FinFET is we have to go with the silicon substrate, and over the silicon substrate we have to grow silicon dioxide or silicon nitride. So here the dimensions of SY, therefore, that I have mentioned, the 400 nanometer, the silicon substrate of 50 nanometer. These are just exemplary parameter we have considered, but this particular paper published by Anderson in 2000. But these dimensions nowadays will change according to at which type nanotechnology we are having fabricated device, maybe at 22 nanometer or 40 nanometer. So these dimensions accordingly change as per ITRS report. So the second step is we have to use this phosphorus type of doped material. So phosphorus is we know that is a pentavalent type of impurity. So if we have to make this FinFET is a N-type. So N-type FinFET, we will go for the pentavalent impurity. If I have to make this FinFET as a P-type, then I will go for the trivalent type impurity, and maybe indium, gallium, or aluminium, or boron type of impurity will use. So these are done with the help of a diffusion process over coin implementation process to make this device doped. Then the next third step is to make the a narrow cut in the channel, as in the IBM structure of FinFET proposed by IBM. We have seen in the gate structure there is a cut at the center, and this is wrapped around with the help of some nitride material. So this is why we have this cut to add the fin that will connect my source and drain. Okay, so how we make this cut, that is again done with the help of lithography process by applying the mask at the top and removal of the sides with the help of etching process, maybe chemical etch or wet etch. If we are using a wet etching process, we use some chemicals, hydrofluoric acid, and sometimes diluted or concentrated. For etching we use a concentrated. So hydrofluoric acid type of etching, as its name is very chemical we are using, so we use it known as wet etching, and here the precisely control of dimensions is not possible. So in the dry etching, where we use some applied voltage, we can say precisely dimensions can be controlled, and we can remove this cut. So why in precisely control of this cut is required? Because if there is, as we previously mentioned, there is a overlapped structure, so sometimes underlapped structure is also there. So if the whole material is not removed with the, if the dose given of this chemical HF chemical that we have to add, if the dose is slightly less than required, then that will be under etched and under gate structure. If the dose sometime slightly increased, then the overlap type of structure will be there. Then we have a FinFET fabrication. Next step is we have to deposit the silicon dioxide. So this is the distance between the spacer and the gate. So we have to grow the silicon dioxide. So at this spacer, we can grow the silicon nitride also, but for the low cost IC we prefer silicon dioxide, because we have a silicon substrate. We can add the oxygen from the external, and there is a chemical reaction in the silicon, and oxygen and silicon dioxide grow automatically. But if we use the spacer of silicon nitride, then this cannot be grown automatically, but the fabrication cost keep on increasing. But the silicon fabrication cost is less in the silicon dioxide, but we have a challenge in terms of its low dielectric constant, so its leakage current might be high. So if we have to go for the low leakage, low power dissipation, we go for the silicon nitride. And also the benefit is silicon nitride can tolerate more temperature as compared to silicon dioxide. So next application step is to uh, remove, once we grow the silicon dioxide, we have to remove the unwanted material with the etching, and we have to also clean the oxide to provide the for the gate oxide. So for that, at the top, we have to boron doping here. So boron is a trivalent type of impurity. So we can say this will be used to dope silicon and germanium material to make the p-type FinFET. Previously, we have seen the pentavalent type of impurity with the diffusion and ion foundation, like phosphorus or arsenide can be used. Then that type of will have a n-type FinFET. In the same silicon wafer, we can grow both n-type and p-type with the different doping techniques. So this is the summary of all the steps we have seen previously. We will start with the silicon on insulator wafer, then deposit the silicon nitride or silicon dioxide. Then we have to use the electron beam lithography to with the help of applying the mask, so that we can selectively decide how much channel length is there, 22 nanometer or 10 nanometer or 32 nanometer. Accordingly, that lithography is set with some mask, and we can from the external we can apply the UV light, or UV light can be used to remove the unwanted material, or chemical or dry etching that can also be applied here. Then we have to deposit a p-type layer with the help of phosphorus type of n-type with the phosphorus and trivalent. Then etching, source and drain. Then again we have to add silicon dioxide as a spacer. Then we have to go for the oxide in side surface of the fin. So finally we will deposit the boron, this doped silicon germanium. So boron that will be given by p-type. So both n-type and p-type can be grown. This is the in fact DC fabrication flow and demonstration of circuit. So these are the same steps that we have discussed previously. We have to start with the conventional silicon on insulator type of technique. Then FinFET there on silicon we have to grow the silicon dioxide or nitride, then this layer. Then this is the conventional steps. This is the further FinFET step. So conventional SOI technique is also used, and this conventional SOI technique means we have to select here single, either partially depleted or fully depleted, and this represents the same picture for the circuit. These are single fin, but in the circuit we require them many FinFETs. So for a simple inverter with n-type and p-type of FinFET, so this give this n-type FinFET, we have p-type FinFET, and inverter require the input from here and output for. So these type of inverter are repeated in the wafer, and from those inverter we can design any type of circuit. We can go for the 2-input NAND gate, and once NAND or NOR is designed, so any type of logic we can design with the these universal gates designed with the FinFET. So first FinFET is used for the inverter design, NAND NOR, and based on all type of logic we can be the standard used for the VLSI circuit design. So next is the spacer lithography. So in the spacer, we use this these are steps required. Like we started the box, silicon on insulated types, then silicon germanium, and then we deposit here silicon and nitride step. So after etching, we have to remove the unwanted and only above this gate we require the this. How we can do this? By applying the mask. So mask, after applying the mask, we have to apply from external UV light or some chemicals or bias voltage to make the remove the unwanted material. So with this, this is the final structure. You can see with the barrier oxide with the fins. So here the two fins are shown just for the how we can go step by step further move to form this. Similarly, multiple fins, 3 fins, 5 fins, 7 fins, they can be designed. So higher the number of fins, higher will be the driving capability. But you can see here the multiple fins require the more number of steps. The fabrication will be little bit complex. Another issue with the multiple fin is in the literature you can see till now only is some of the people they reported the 3 and 5 and 7 fins structure also, but from circuit design point of view for a reliable circuit design, 3 fins are highly preferred. If we have 5 fins, then the complexity is very high. So that is not, although they work well, but preferably people use 3 fins for the circuit design. Why 3 fins? Because of its, as I discussed previously, the parasitic capacity can be removed automatically, and their fabrication issues is also a little bit simple. Then these are the some of the FinFET fabrication steps with the dimensions and also with the time. So how much time we which chemical or bias voltage or like for the etching we use the hydrofluoric acid. For how much time we have applied this chemical or bias voltage that is used. So we start with the lot with if we have 70 nanometer of silicon and 150 nanometer box. Then for the pre-oxidation cleaning, 5 minutes we use this material, and this is the 1:200, 2 minutes for the DHF. This is DHF is dilute hydrofluoric acid. So if I have a concentrated hydrofluoric acid, then definitely the time will be a little bit small. Then we have thinning through the oxidation, then oxide removal with the help of dilute hydrofluoric acid, then silicon. So how much time required for which material, that is mentioned here. So this is the fabricated data for a FinFET. So we also have here walk H. So that is a bottom anti-reflection coating. So in the FinFET, this technique is the bottom anti-reflection coating we use to in the conventional MOSFET. When I start lecturing, we have seen there is a direct path from a source to body and drain to body. So that is the limitation that enhance my leakage current. So in the FinFET, we use this bottom anti-reflection coating with some material having the work function different from the channel material. So this reflection, what is the role of this bottom anti-reflection coating is to minimize my leakage current. So the biggest advantage of FinFET we are discussing is it can work for the low power. If we have to go for low power, its leakage must be as small as possible. Some of the leak is minimized because of its structure self-aligned that we have discussed. Another factor why the leakage current is minimum in the FinFET is because of this BARC process. So we also have this HM mask where we have a hard mask used in the etching. So we have a resistor strip also. Then for the removal of different structure. So this is the silicon plasma etching. with the different hard mask, and ultimately we have to come up with the final this type of silicon fin that is connecting with the source and then the center part is the fin. So there are some other steps that we use the amorphous silicon deposited. So gate etch, screen etch. So there are so many number of steps. I think you need not to uh, follow all the steps because these steps are the experimental. This is the experimental data used in the fabrication. But all these steps you can do in the tool itself also with the help of Silverco. There is a Athena part is there. In the Athena, you can do all these steps with the and you can design your device. So there are so many here. Around 50 steps are given for the different FinFET design. So these are the not only 50 steps. These steps for final device. They are repeated. I mentioned double gate FinFET, triple gate, quarter gate. How many number of gates are there? Accordingly, the number of steps keep on repeated, and the final device structure we came up with this type of. This is the final cross section of the fin channel through the gate. So this is all about the FinFET fabrication. So next is device modeling, FinFET modeling. So I think time is already 1:20. So let me skip the modeling part and we can discuss this in some other lecture. So let me come up with some conclusion what we can do. There are some results. Due to limitation of time, we can skip the modeling part. Okay. Let's come to this. What are the research directions? And so we have in the this domain, we seen the conventional single gate most devices. They are now further with the double gate or FinFET. Then now currently you can see this gate all round type of structure there that is under the research. So nanowire, CNT FET, nano seed, nano ribbon. So all those type of structures they are under the research for to analyze its performance in terms of ion ratio. So how their parasitic capacitances can be minimized, how the leakage current can be minimized, how ion can be enhanced, how surface hold slope can be improved. So all those parameters can be improved with the gate all type of structure. So those who are working this like tunnel feedback transistor. So these type of structure can gate all around structure is a general term and you can modify your device to enhance the parameter. So this is the gate all around type of structure. So let me see the facility is required if this type of work you want to do or analytical modeling or basic analysis. We require the MATLAB or Mathematica. If you propose a new device, ultimately the conventional MOSFET they have the well established mathematical expression available in the textbook for drain current and potential. So those current expression of potential expression you can modify according to your device structure, maybe double gate or triple gate. With the MATLAB or Mathematica, you can solve the mathematical expression and you come up with the compact device model. So those compact device model, they are based on physics based model, can be lookup table based model or numerical model or analytical model. So those analytical model or numerical model you can validate with the either experimental data or you can validate with the help of some TCAD simulations like you have Silverco tools, Dyrus tool, Linux based PCs are required to install these tools and you can and compare your result mathematical and modeling result with the softwares. Or if you have to go for the circuit design based on these nano devices, you have to go for the HSpice or Cadence tool is required. Then backend tools like layout design tool, network analyzer for some experimentally characteristics you can analyze with the probe station. So let me summarize what we did in this talk. We started with the scaling trend of of conventional MOSFET, that is having a limitation below 50 nanometer, we cannot go. So this FinFET device can be used to lead the scaling further below even 10 nanometer. Then leakage current and sound channel effects, that have been the problem that can be minimized in these nano devices. Then analytical modeling results, although I have not discussed the modeling part, but you can do this and validate your result with the TCAD simulation and experimental data. Then further proposed research in this area can be gate all around type of structure. So gate all around type may be tunnel FET, nanowire, nano seed. So all those structures you can analyze. So with this, I thank you all for your patience listening. So now the house is open. If you have any query, we can discuss. Yes, any question from the participants?
Any questions from the participants?
So, what are the merits and demerits of using quad gate and pi gate FinFET?
Actually, pi gate structure having the limitation because at the bottom, as I mentioned, the silicon dioxide is highly used for the fabrication, because if we have a silicon substrate, we can add the oxygen and silicon dioxide can grow automatically. Okay, so during the fabrication, uh, uh, oxygen can be applied on the silicon wafer from the top, front, and back, but it's very difficult to add the oxygen from the bottom side. So that's why pi type structure is used so that silicon dioxide grow all three sides from the but bottom we keep it open. So that is the challenge in the fabrication. That's why we use the this is the challenge in the quarter gate, where we have the gate from all the side, that is not using the conventional planar technology, but with the vertical technology. uh, from all four sides we can use the this gates with the growing the silicon dioxide from all side, or we can even use the silicon nitride. So with those type of structure, we have advantage due to for quarter type structure. Driving current capability is very high, switching speed is very high, but the limitation is in terms of developing its mathematical model. You know, you have a if you have a mathematical model for the conventional single gate MOSFET, you have a in the drain current expression you have the gate voltage VG. If you have a double gate, you have, in same mathematical equation you have to apply VG1 VG2 and calculate the whole its potential and electrical expression. If you go with triple gate, you have to apply VG1 VG2 VG3, quarter gate VG1 for. My thing is I want to stress, keep on number of gates, its complexity is keep on increasing, so manually calculations, analytical modeling is not possible in that case. So at the same time, its fabrication issues also there in terms of its number of steps. So you have seen 50 steps I have shown required for a single FinFET. So if we have a multi-fins or a quarter type, then those steps may increase up to 200 or 250 or 300. So keep on increasing the number of steps means we keep on increasing its cost of the device. So sometimes cost is very critical factor. So I hope it's clear to you. If you have any further doubt, you can ask. Is it clear? Your query?
Yes, sir. Thank you, sir.
Okay. Any other question?
Hello.
Yes, yes.
Hello. Hello. Sir, I'm Jitendra, sir.
Yes, Jitendra and Ajay both are talking. So one by one, you can have your question. So,
Okay, sir.
Jitendra, yes, you can take the first your question.
Yes, sir.
Yes,
Yes, sir.
Jitendra, are you?
Yes, sir. As you told me, sir, told us that using odd number of fins in the FinFET, we
Uh-huh.
can remove the parasitic capacitance.
Yes.
Does it remove junction capacitance as well as overlap capacitance using odd number of fins?
No, no. Junction capacitance is something different. Junction is where my two different material N and P is joining, and
Yes.
space charge is in between there. So junction capacitance is remain there that we can remove with the help of high doping or with the help of external bias, applied bias voltage. But parasitic capacitance is that we can minimize with the help of all odd number of fins. So in the these FinFET, you might see moderate doping or low doping type of structure also used. So in those structures, this junction capacitance is a little bit high.
Okay, okay. Thank you, sir. Thank you, sir.
Yes, Ajay Kumar, you have a query?
Hello.
Yes, yes, Ajay. Go ahead.
Good afternoon, sir. Sir, my question is related to substrate material. Sir, as you
Substrate.
said in case of as you said in case of FinFET technology, we use SY structure.
Yes.
Sir, what is the issue with bulk substrate?
Yeah, your question is very good. If we use the SiFET technology with the conventional MOSFET, then also we can minimize leakage current. But that is up to some extent. That is, if we use the SY technology with the bulk, so because in the SY my back leakage is removed, but the bulk MOSFET my substrate is body part is bulky, na. So due to bulky, there is another effect known as body effect. Source,
Yes, sir.
source, body, and drain, and backside body. So that body effect we cannot minimize with the SI technology, but we can minimize the back leakage. Now come to the FinFET. If in the FinFET we have a SY as well as at the top of SY we are modifying our structure from the planar to vertical structure. So body effect that we have conventional MOSFET, though that can be minimized with the FinFET vertical structure, and leakage can minimized with the back leakage. I am oxide SY mean back leakage we are minimizing with the oxide thickness. Is it clear?
Yes, sir. Sir, one more question.
Yes, yes.
Sir, sir, can I speak in Hindi? Because
Yeah, sure, sure, sure. हिंदी में पूछिए, नो इशू.
ओके सर. हाँ हाँ. सर, जैसे सिल्वाको टेकैड सिमुलेशन जो सॉफ्टवेयर है. हाँ सर, तो मैं सिल्वाको टेकैड यूज करता हूँ. सर, इशू ये आ रहा है कि अभी जैसे जहाँ मैं यूज कर रहा था वहाँ लाइसेंस एक्सपायर हो चुका है.
ठीक है.
तो सर, अगर आपके पास मतलब जैसे किसी के पास कोई नोवेल आइडिया है या कुछ भी है वो सिमुलेट करना चाह रहा है तो और उसको वर्क पब्लिश करना है,
ठीक है.
तो सर क्या कर सकते हैं फिर हम इस केस में? जैसे मुझे कहीं कोई जैसे फाइंड आउट नहीं मिल रहा कि मैं कहाँ इसको यूज करूँ.
We have a licensed version in our institute. So one thing you can do, you can either visit the our institute and you can work here, but due to COVID, it's difficult to travel for you, and even institute may not allow to stay in the hostel. So if you still want to work virtually, you can access this our license from here with the team viewer or some other virtual mode. So you can work. We can help you in this way. No, no issue. From which institute you are working?
Sir, I am from Department of Electronic Science, Kurukshetra University, Kurukshetra.
Kurukshetra University. So
Yes, sir.
Kurukshetra is near to Chandigarh, so you can visit the later sometime, or you can contact me on email or phone. We will try to address your problem.
Okay, sir. Thank you so much, sir.
Any other question?
I think, sir, there is no other questions from the participant side.
Okay, if there is no more question, then let me thanks all the participants for their patience listening. I hope they have gained something. If further they have any query, they can write email to me, or they can discuss whatever the questions they have. Or if they want to work in this area, they can also visit our lab, or we can help you out. So I also would like to thank Dr. Ashish Raman and Dr. Mamta Khosla, who are coordinator of this course, for giving me this opportunity to interact with all of you. So thank you, Sahil. You also
Thank
for
Thank you so much, sir, for this wonderful session. It's very informative and helpful for all the participants. Thank you so much, sir, for your
Okay,
time.
thank you one and all. Thank you very much.
Okay, sir. Thank you, sir. तो सर अब क्लोज करें सेशन.
Yes, you can end.
Okay, sir. Okay.